Everything you were taught about the emptiness of space is wrong, and the people who proved it was wrong have known for decades. In 2012, a team at the University of Michigan pointed the Subaru telescope at a patch of sky between two galaxy clusters and measured how the light from 40,000 background galaxies was being warped, bent, distorted by something massive sitting between those clusters that no telescope could see. When they mapped the distortion, a shape emerged, a thread, a filament of invisible matter 18 megaparsecs long, stretching 60 million light-years between Abell 223 and Abell 2233, containing somewhere between 65 and 98 trillion solar masses of material. They had photographed something that should not have been visible, a strand of dark matter connecting two clusters of galaxies like a nerve fiber connecting two regions of a brain. That image has been confirmed and refined. In January of 2025, a team in Milan pointed the Very Large Telescope at the same kind of structure for 150 hours straight and produced the sharpest image of a cosmic web filament ever captured. 3 million light-years of invisible scaffolding made visible by the faint glow of hydrogen gas draped over it like frost on a wire. The light in that image traveled 11 billion years to reach the detector. But here is the part nobody told you. These filaments are not rare. They are not unusual formations found in exotic corners of the universe. They are everywhere. Every galaxy in the observable universe, all 2 trillion of them, sits on a filament. Every filament connects to other filaments at dense intersections called nodes, where galaxy clusters form. Between the filaments are voids, bubbles of almost pure emptiness, hundreds of millions of light years across. The whole thing, when you map it, looks like a 3-dimensional web, a network of threads and junctions that stretches across the entire observable universe. And in 2020, an astrophysicist named Franco Vazza and a neurosurgeon named Alberto Fleti ran the same mathematical analysis on this cosmic web that cosmologists use to study the large-scale structure of the universe. They ran it on slices of human brain tissue, the cerebellum, the cortex. They compared the power spectrum of density fluctuations in neural tissue to the power spectrum of density fluctuations in the cosmic web. The two curves were nearly identical, not similar, not loosely comparable, statistically indistinguishable across 27 orders of magnitude in scale. That finding was published in Frontiers in Physics, peer-reviewed. The data is public, and you almost certainly never heard about it. The question this video is going to take apart is not what the cosmic web is. You can get that from a 10-minute explainer. The question is why the largest structure in the observable universe, a structure built from a substance that has evaded every particle detector ever constructed, produces the same mathematical signature as the one structure in nature that processes information, and why the answer to that question is something the scientific establishment has been extraordinarily quiet about. This starts, like too many important things in science, with someone who was right and was punished for it. In 1933, a Swiss astronomer named Fritz Zwicky was working at Caltech, studying a cluster of about 1,000 galaxies in the constellation Coma Berenices, the Coma cluster. Zwicky was not the kind of person institutions love. He was brilliant, confrontational, and had a habit of being correct about things before anyone else. which is one of the most unforgivable qualities in professional science. He applied a technique called the virial theorem to the velocities of galaxies in the cluster. The math was straightforward. You measure how fast the galaxies are moving. You calculate how much mass is needed to keep them gravitationally bound. Then you compare that to the mass you can actually see in stars and gas. The numbers did not match. They did not come close to matching. Zwicky calculated that the Coma cluster contained roughly 400 times more mass than its visible matter could account for. 400 times. He was using an inaccurate value for the Hubble constant, so the real ratio was closer to 50 or 60 to 1. But the call finding was correct and devastating. The vast majority of the mass holding that cluster together was invisible, could not be seen with any telescope, could not be detected with any instrument available, was only knowable through its gravitational effects on things you could see. Zwicky called it Dunkel Materie, dark matter. He published the result in Helvetica Physica Acta and moved on to his next discovery, because Fritz Zwicky was always moving on to the next discovery. Within a few years, he would predict the existence of neutron stars, predict that dying massive stars produce supernovae, and predict that galaxies could act as gravitational lenses, bending light from objects behind them. All three predictions were confirmed. He was, by any reasonable measure, one of the most prescient astrophysicists of the 20th century. The scientific community ignored him, not politely, not through the quiet indifference that greets mediocre work. They actively despised him. Zwicky called his Caltech colleagues spherical bastards, which he explained meant they were bastards no matter which way you looked at them. He accused Walter Baade, another Caltech astronomer, of being a Nazi. He accused others of stealing his ideas. He was banned from the 200-inch Palomar telescope, the most powerful instrument in the world at the time, by colleagues who wrote a special rule to keep him away from it. He spent decades in a basement office cataloging galaxies that no one asked him to catalog, compiling data that no one wanted to read. His daughter Barbarina said later that he was actually very decent and kind, that colleagues would scatter when they saw him coming down the hallway, that the abrasiveness was real, but so was the decency, and the scientific establishment chose to see only the abrasiveness because it was easier than admitting that the man in the basement had discovered something that would take them 40 years to accept. Zwicky died in 1974. He never saw his dark matter hypothesis confirmed. He never saw the cosmic web. He never saw the Coma cluster, the exact cluster he studied in 1933, directly imaged for dark matter filaments in 2024 by a team at Yonsei University using the same Subaru telescope that produced the first filament image 12 years earlier. 91 years, same cluster, same invisible mass, same unanswered question about what it actually is. But before the cosmic web could be mapped, the dark matter Zwicky had found needed to be confirmed by someone the establishment could not dismiss. That person turned out to be someone the establishment tried very hard to dismiss anyway. Vera Rubin wanted to study astronomy from the time she was 10 years old, watching stars through her bedroom window in Washington, D.C. She applied to graduate school at Princeton in 1948. Princeton sent back a letter explaining that women were not admitted to the astronomy program. They would not admit women until 1975. She went to Cornell instead, where she studied under Philip Morrison and Hans Bethe. Her master's thesis, presented at the American Astronomical Society in 1950, suggested that galaxies might rotate around some unknown center rather than simply expanding uniformly. The room was largely dismissive. She was 22, pregnant, and proposing something that sounded uncomfortably like a challenge to the prevailing cosmological model. She moved to Georgetown University, completed her PhD under George Gamow, and then spent years looking for a research problem that was important enough to matter, but unfashionable enough that no one would fight her for telescope time. In the late 1960s, she found it, working with Kent Ford, an instrument builder at the Carnegie Institution, who had built an image tube spectrograph far more sensitive than anything available at the time. Rubin began measuring the rotation curves of spiral galaxies. This is conceptually simple. You point a spectrograph at a galaxy and measure how fast the stars at different distances from the center are orbiting. Newtonian gravity makes a clear prediction. Stars farther from the center, where there is less visible mass interior to their orbit, should be moving more slowly, like planets in the solar system. Mercury is fast. Neptune is slow. That is not what Rubin and Ford found. Their 1970 paper on Andromeda, the nearest large spiral galaxy, showed that stars at the edges of the galaxy were orbiting just as fast as stars near the center. The rotation curve was flat, not declining. Flat. This should not be possible unless the galaxy is embedded in an enormous halo of mass that extends far beyond its visible edge. Mass that cannot be seen. They published more galaxies. By 1980, they had measured rotation curves for 21 spiral galaxies. Every single one showed the same flat curve. Every one required roughly 10 times more mass than could be accounted for by visible stars and gas. The conclusion was inescapable and exactly what Zwicky had said 47 years earlier. The universe is dominated by invisible matter. Galaxies are not mostly stars. They are mostly something else, something dark. The establishment pushed back, but not for long. The data was too clean. Ford's spectrograph was too good. And Rubin, unlike Zwicky, was impossible to dismiss as a crank. She was meticulous, careful, self-deprecating, and devastatingly correct. Within a few years, flat rotation curves became one of the foundational pieces of evidence for dark matter in the standard cosmological model. Rubin never received the Nobel Prize, not in the 1980s, not in the 90s, not in 2016, when she died on Christmas Day at the age of 88. The Physics Nobel has been awarded to over 200 people. 3 of them are women. Rubin, who provided some of the most important observational evidence for the existence of dark matter, a discovery that reshaped the entire field of cosmology, was not among them. Multiple physicists, including Lisa Randall at Harvard, have publicly called the omission a grave injustice, likely rooted in gender bias. The Vera Rubin Observatory in Chile, the first national observatory in the United States, named after a woman, began its commissioning phase in 2024. The recognition came. It came decades too late for the person it was meant to recognize. But Rubin's rotation curves proved something about individual galaxies. They showed that galaxies are wrapped in dark matter halos. What they did not show was the larger pattern, the web. To see that, you needed to zoom out, way out, and the people who did that were about to discover something that made dark matter halos look almost comforting by comparison. In the early 1980s, Margaret Geller and John Huchra at the Harvard-Smithsonian Center for Astrophysics began one of the most tedious and transformative projects in the history of observational astronomy, the CFA Redshift Survey. The idea was straightforward but brutal in execution. Point a telescope at galaxies, measure their redshift, one at a time, 20 minutes to an hour per galaxy. Use the redshift to calculate distance, plot the galaxies in 3 dimensions, see what the large-scale structure of the universe actually looks like. Huchra was the kind of astronomer who does not exist anymore. He observed 130 nights in a single year. He kept his Teamsters union dues current so he could drive a truck if astrophysics did not work out. He cooked Thanksgiving dinners for foreign students who had nowhere else to go. He measured galaxy after galaxy after galaxy, accumulating redshifts the way other people accumulate frequent flyer miles, with obsessive dedication and no guarantee that anything interesting would emerge. Something interesting emerged. In 1986, their graduate student, Valérie de Laparaine, plotted the first slice of the survey, just a thin wedge of the sky a few degrees wide. Instead of a uniform scatter of galaxies, the plot showed something no one expected. The galaxies were clustered on the surfaces of enormous bubble-like structures, voids, empty regions hundreds of millions of light-years across, surrounded by thin walls and filaments of galaxies. It looked like the universe had been inflated from the inside, matter pushed to the edges of expanding bubbles and left there. Huchra looked at the data and assumed he had made an error somewhere in the reduction pipeline. He went back through the observations. No error. Geller looked at the same data and realized the universe had a structure no one had predicted, not a uniform distribution, not a random scatter, a pattern. By 1989, with 18,000 galaxy redshifts compiled, a heroic quantity at the time when each measurement required manually positioning a telescope and waiting for photons to accumulate, they published the discovery of what they called the Great Wall, a filament of galaxies 500 million light-years long, 300 million light-years wide, and 15 million light-years thick, the largest coherent structure anyone had ever observed, stretching across the full extent of their survey. Geller described the galaxy distribution as looking like a slice through the suds in a kitchen sink. Bubbles, surfaces, filaments, a foam. The scientific response was immediate and electric. But the theoretical explanation took years. The critical framework arrived in 1996 when Richard Bond, Lev Kaufman, and Dmitry Pogosyan at the Canadian Institute for Theoretical Astrophysics published a paper in Nature titled "How Filaments of Galaxies Are Woven into the Cosmic Web." They showed that this filamentary structure is not an accident of galaxy formation. It is encoded in the initial density fluctuations of the very early universe, tiny quantum ripples imprinted on matter in the first fraction of a second after the Big Bang. Gravity takes those ripples and amplifies them over billions of years. Matter flows out of underdense regions and onto overdense ones. Filaments form along the ridges of the initial density field. Clusters form at the intersections. Voids expand as matter drains away. The whole structure is a gravitational inevitability written into the initial conditions of reality itself. The pattern of the cosmic web was determined in the first trillionth of a trillionth of a second, and everything since has been gravity doing the math. Bond, Kaufman, and Pogosyan coined the term cosmic web. Kaufman died in 2009 at 52, before the term became standard in every cosmology textbook. Geller, whose observational work first revealed the structure, was never given tenure at Harvard. She received a MacArthur Fellowship, one of the most prestigious honors in American science, and Harvard still would not make her a full professor. Huchra, legendary for observing the 130 nights in a single year, cooking Thanksgiving dinners for foreign students, and keeping his Teamsters union dues current so he could drive a truck if astrophysics did not work out, died unexpectedly in 2010 at 61 of a heart attack. The universe's largest pattern was mapped by people who were either ignored, excluded, or taken too early. Within a decade of Bond's paper, cosmological simulations had confirmed the theoretical picture in extraordinary detail. The Millennium Simulation, completed in 2005 by Volker Springel and colleagues at the Max Planck Institute for Astrophysics in Garching, was the most ambitious computational project in astrophysics history at that time. 10 billion dark matter particles tracked through 13.7 billion years of cosmic evolution. In a cube, roughly 2 billion light years on a side. The simulation ran for over a month on the Institute's supercomputer and generated 25 terabytes of data. When the results were rendered, the structure that emerged was unmistakable. Filaments, nodes, voids, the cosmic web in exquisite detail, generated from nothing but the laws of gravity, the expansion of the universe, and the initial fluctuations measured by satellite observatories. It matched the large-scale structures seen in the Sloan Digital Sky Survey with disturbing precision. The simulation has since been cited in over 950 published papers, making it the most impactful astrophysical simulation ever produced. But the Millennium Simulation only tracked dark matter. It could not model gas, star formation, or the complex physics of galaxy evolution. That came with Illustris DNG, launched in 2018 by a collaboration including Springel, Dylan Nelson, Annalisa Pilipich, and others. Illustris NG is a full magneto-hydrodynamical simulation, meaning it models dark matter, gas, stars, magnetic fields, supermassive black holes, and their interactions simultaneously. Its three nested volumes, TNG50, TNG100, and TNG300, provide views of the cosmic web at progressively larger scales, and the results are publicly available. By January 2025, over 1,000 papers had been published using TNG data, and the simulations had demonstrated something critical for our story. The cosmic web environment does not just correlate with galaxy properties, it causes them. Galaxies and dense filaments form differently, evolve differently, and die differently than galaxies in voids. The web is the dominant variable. But the Great Wall, as dramatic as it was just the visible part. Galaxies are bright. You can see them. What you cannot see, what makes up the bulk of the filaments, is dark matter. And this is where the story shifts from discovery to something considerably more disturbing. The cosmic web is not a web of galaxies. Galaxies are decorations on the web, beads strung along threads. The threads themselves, the actual structural filaments that hold the whole thing together, are made of dark matter. This was predicted by every major cosmological simulation and confirmed by the direct imaging results. When Dietrich's team measured that first filament between Abell 222 and Abell 223 in 2012, the X-ray observations showed that hot gas accounted for no more than 9% of the filament's mass. The rest, more than 90%, was dark matter. You could see the gas because it glows in X-rays. You could measure the dark matter only by the way it bent light from galaxies behind it. The scaffolding of the universe is invisible. The galaxies you can see are just the frost that formed on it. The numbers that describe the scaffolding are difficult to process. Typical dark matter filaments stretch 50 to 80 megaparsecs, which translates to roughly 160 to 260 million light-years. Their widths are 1 to 2 megaparsecs, 3 to 6 million light-years. This gives them aspect ratios of 25 to 1 or even 80 to 1. They are proportionally thinner than a human hair. The longest confirmed filament discovered in February 2025 stretches approximately 400 megaparsecs, 1.3 billion light-years. Light that left one end of that filament when the most complex life on Earth was single-celled organisms in shallow seas would still not have reached the other end today. Filaments contain roughly half of all mass in the universe, while occupying just 6% of its volume. Cosmic voids fill 76% of space, but hold only about 15% of the mass. Galaxy clusters, the dense nodes where filaments intersect, pack 10% of the universe's mass into 0.02% of its volume, and approximately 82% of all the stellar mass in the universe. Every star in every galaxy you have ever seen a picture of lives on a filament. The Sloan Digital Sky Survey alone catalogued 63,391 filaments in its survey volume. Extrapolating to the full observable universe suggests millions of filaments exist, forming a structure so vast that the only way to visualize it is to step back until galaxies become points of light and the pattern emerges. A web, a network, threads and junctions stretching in every direction, surrounding bubbles of emptiness that dwarf anything within them. To put the emptiness in perspective, consider the Boots void, discovered accidentally in 1981 by Robert Kirshner, Augustus Oemler, Paul Schechter, and Stephen Schechtman during a redshift survey. It is 330 million light-years across, a sphere of almost nothing. Inside it, astronomers have found approximately 60 galaxies. In a region that size, based on the average density of the universe, you would expect about 2,000. The void is not entirely empty, but it is close enough to empty that it has been called a supervoid, one of the largest individual structures in the observable universe, defined not by what it contains, but by what it lacks. If you lived on a planet inside the Boots void, your experience of the universe would be profoundly different from ours. You would look up at the night sky and see your own galaxy, and then almost nothing, a handful of dim smudges scattered at immense distances. No Milky Way band of stars from neighboring galaxies, no rich cluster on the horizon. You would have no experiential reason to suspect that just beyond your visible horizon, in every direction, an unimaginably vast network of matter connects everything to everything else. You might develop astronomy. You might measure the cosmic microwave background and deduce that the universe was once hot and dense. But the large-scale structure, the web the filaments, the nodes, the architecture that defines how the universe actually works, would be invisible to you. Not because your instruments were not good enough, because there would be nothing nearby to see. You would be wrong about the nature of reality, and you would have no way of knowing it. That thought experiment is not entirely hypothetical. For most of human history, we were in an analogous position. We could see galaxies, we could count them. We assumed they were scattered more or less uniformly, like raisins in a pudding. The cosmic web was invisible to us, not because it was hidden by anything exotic, but because mapping it required measuring the distances to tens of thousands of galaxies, one by one, and nobody had done that yet. The architecture of reality was there the entire time. We just had not looked carefully enough. The question of where we sit in this web has its own answer. In 2014, Brent Tully, Helene Courtois, and their colleagues published a landmark paper mapping what they called the Laniakea supercluster. Using peculiar velocity flows, the motion of galaxies over and above the expansion of the universe, they traced the gravitational basin that contains our galaxy. Laniakea means immense heaven in Hawaiian. It spans 520 million light years and contains approximately 100,000 galaxies, all flowing toward a gravitational center called the Great Attractor. The Milky Way sits on the outskirts, on a filament, connected to the local sheet, a galaxy wall about 34 million light years across, which itself feeds into the larger structure of Laniakea. You are on a filament right now. The Milky Way is not floating in empty space. It is embedded in a thread of dark matter that connects it to the Virgo cluster and beyond. And that thread is part of a structure that extends across 500 million light years in every direction. High-velocity hydrogen clouds are raining onto our galaxy at roughly 0.2 solar masses per year. Fragments of cosmic wet gas that are literally feeding the Milky Way, keeping it alive. Without those filaments, without that supply line of gas, star formation in our galaxy would eventually slow and stop. The web is not out there somewhere. It is here. It is the thing keeping the lights on. But there is a problem with all of this. A problem so fundamental that it should make everything I have just described feel unstable. We know the web exists. We have photographed it. We have simulated it. We have measured its mass, its temperature, its density, its effect on galaxy formation and evolution. We know that 85% of its mass is dark matter, and after more than 90 years of searching across dozens of experiments costing billions of dollars, using the most sensitive instruments ever constructed by human beings, we have never detected a single particle of the substance that makes up most of the universe. That is not a gap in our knowledge. That is a crisis. The search for dark matter particles has been one of the most sustained and expensive experimental campaigns in the history of physics. The leading hypothesis for decades was that dark matter consists of WIMPs, weakly interacting massive particles, predicted by supersymmetric extensions of the Standard Model. WIMPs were attractive theoretically because they naturally produced the right amount of dark matter in the early universe, a coincidence so convenient that physicists called it the WIMP miracle. The idea was simple: build a tank of ultra-pure liquid xenon, put it deep underground, shielded from cosmic rays and radioactive contamination. Wait for a dark matter particle to collide with a xenon nucleus, Measure the tiny flash of light and charge that the collision produces. The LUX experiment at the Sanford Underground Research Facility in South Dakota used 370 kilograms of liquid xenon. It ran from 2013 to 2016. It found nothing. The XEnon experiments at Gran Sasso National Laboratory in Italy escalated from XEN ON10 to XEN ON100 to XEN ON1T, the first ton-scale dark matter detector in history, containing 3.5 tons of liquid xenon. XEN ON1T reported a small anomalous excess in 2020, a 3.5 sigma signal that generated enormous excitement. It was later attributed to trace contamination by tritium. The current XENONT, using 5.9 tons of xenon, has found nothing. Panda X, operating in the deepest underground laboratory in the world, the China Jinping Underground Laboratory, beneath 2,400 meters of marble, has run through 3 generations of detectors. Nothing. The Large Hadron Collider at CERN has been searching for dark matter particles since 2010. The idea is different, but complementary. If dark matter particles interact with normal matter even weakly, then smashing protons together at nearly the speed of light should occasionally produce them. You would see their signature as missing energy in a collision, momentum that goes unaccounted for because the dark matter particle passes through the detector without interacting. The LHC has found the Higgs boson, confirming the Standard Model's last missing piece. It has found no supersymmetric particles, no dark matter candidates, no physics beyond the Standard Model at all. Thousands of physicists, billions of dollars, the most powerful particle accelerator ever built. And as far as dark matter is concerned, the answer has been silence. Then came LZ. The Lux Zeppelin experiment is the most sensitive dark matter detector ever constructed. 7 tons of liquid xenon surrounded by a skin detector and a neutron veto, buried a mile underground in the same South Dakota mine where Lux operated. In December of 2025, the LZ collaboration published results from 417 live days of data collection. They searched for WIMPs across the broadest mass range ever explored, with sensitivity 4 times better than any previous experiment. They found 0 dark matter particles. What they did find was something beautiful and deeply inconvenient. LZ detected solar neutrinos through coherent elastic neutrino nucleus scattering at 4.5 sigma significance. Neutrinos from the core of the Sun passing through the rock and the xenon and leaving just enough of a signal to be measured. This is extraordinary physics. It is also a death sentence for the current generation of detection technology. Those neutrinos create what physicists call the neutrino fog, an irreducible background of signals that look exactly like what a dark matter particle would look like. Push the detector sensitivity any further, and you cannot tell the neutrinos from the dark matter. You are listening for a whisper in a room that has a permanent, unremovable hum at exactly the same frequency. The next generation of experiments, XLZD and DarkSide 20K, will attempt to push through the fog using different techniques and different target materials. But the classical WIMP, the particle that was supposed to make everything neat, is running out of parameter space. If it exists in the mass range that the WIMP miracle predicts, LZ should have seen it. It did not. And this is where it gets worse, because the failure to find dark matter is not just a problem for particle physics. It is a problem for everything I have described in this video so far. We have mapped the cosmic web. We have photographed its filaments. We have measured the gravitational lensing distortions that prove the filaments are real and massive. We have watched them feed galaxies with streams of gas. We have traced how they determine the spin, the orientation, the life, and the death of every galaxy in the observable universe. We have built this entire picture of cosmic architecture on a substance that, as of December 2025, we cannot confirm is made of particles at all. The bullet cluster is the reason physicists are not ready to abandon dark matter despite the detection failures. Catalogued as 1E0657-558. It is actually two galaxy clusters that collided at roughly 4,500 kilometers per second, approximately 150 million years ago. The collision was observed in X-rays by the Chandra telescope. When two galaxy clusters collide, the hot gas in each cluster, which makes up most of the normal matter, slams together and slows down. Electromagnetic friction. The gas interacts with itself. You can see this in the X-ray image as a bright region between the two clusters, where the gas piled up like a traffic jam. But the gravitational mass, mapped through weak lensing of background galaxies by Douglas Clow and an international team, did not pile up. It sailed straight through, ahead of the gas, on both sides. The mass and the gas separated, cleanly, unambiguously. Clow published the analysis in the Astrophysical Journal in 2006, calling it a direct empirical proof of the existence of dark matter. The offset between the gravitational mass and the visible gas was measured at 8 sigma significance. 8 sigma. In particle physics, 5 sigma is considered discovery. This is beyond discovery. This is settled. If gravity were the whole story, if there were no dark matter, and the gravitational effects were just a modification of Newtonian mechanics, the lensing signal should follow the gas. It does not. It follows the galaxies, which passed through each other collisionlessly, exactly as dark matter would. The galaxies are tiny by comparison. They barely interact during the collision. They fly through like bullets through smoke, and the gravitational mass flies with them, not with the gas. The bullet cluster is why physicists say dark matter must be real, even though they cannot find the particle. The gravitational evidence is overwhelming. The particle evidence is zero. That tension should bother you more than it does. We are not talking about a minor discrepancy at the margins of detection. We are talking about 85% of all matter in the universe. We can see what it does. We can measure its effects with extraordinary precision. We have photographed the structures it builds, structures that stretch for billions of light years, that contain half the mass of everything that exists. And we have no idea what it is. Not a strong suspicion. Not a leading candidate with partial evidence. After 92 years, dozens of experiments, and billions of dollars, we have exactly as much direct particle evidence for dark matter as Fritz Zwicky had in 1933, which is to say, none. Alternatives exist, but none of them are comfortable. MOND, Modified Newtonian Dynamics, proposed by Mordechai Milgram in 1983, modifies the law of gravity at extremely low accelerations, below about 1.2 times 10 to the minus 10 meters per second squared. MOND is remarkably good at predicting galaxy rotation curves from visible matter alone, without any dark matter. It is also a complete failure at the bullet cluster and at cosmological scales. It cannot explain the cosmic microwave background power spectrum. It cannot reproduce the large-scale structure of the universe. It fixes one problem while breaking a dozen others. Eric Verlinder's Emergent Gravity, published in 2016, is more radical. Verlinde proposes that gravity is not a fundamental force at all, but an emergent phenomenon arising from quantum information. In this framework, what we call dark matter is actually an effect of the universe's information content, a manifestation of the entanglement entropy of the vacuum. The equations naturally recover MOND-like behavior at galactic scales, while potentially explaining dark energy as well. Tests against gravitational lensing data from 30,000 galaxies have been promising, but the theory is incomplete, mathematically contested, and has not been developed to the point where it can make the kind of precise predictions that the standard cold, dark matter model can. So here is where we stand. The cosmic web is real. It has been photographed. Its filaments span hundreds of millions of light years. They contain half the mass of the universe. They feed, shape, and kill galaxies. The substance composing 85% of these filaments has been searched for with the most sensitive instruments in human history. Every search has returned nothing. The best alternative theories either fail at cosmological scales or remain incomplete. And the structures that this unknown substance has built, the pattern it has created across the entire observable universe, bear a mathematical resemblance to the one structure in nature that we know processes information. But before we get to that resemblance, you need to understand something that most popular accounts of the cosmic web leave out entirely, because the standard version of this story presents the web as scaffolding, a structure, a static framework that galaxies happen to live on, the way buildings sit on a street grid. That is not what the cosmic web is. The cosmic web is not a passive structure. It is the dominant influence on how galaxies form and evolve in the universe. It builds them, it feeds them, it determines how they spin, and when it is done with them, it kills them. The mechanism is called cold flow accretion, and it is one of the most important discoveries in galaxy formation theory in the last 20 years. Here is the problem it solves. Galaxies form stars. To form stars, they need gas, specifically cold hydrogen gas that can collapse under its own gravity and ignite nuclear fusion. A galaxy like the Milky Way converts roughly 1 to 2 solar masses of gas into stars every year. It has been doing this for over 13 billion years. If you add up all the gas that was in the Milky Way's disk when it first formed, it runs out in a few billion years. The gas supply should have been exhausted long ago. We should be living in a dead galaxy. We are not. Something is replenishing the fuel. That something is the cosmic web. In 2003, Yuval Birnbaum and Avishai Dekel at the Hebrew University of Jerusalem published a paper that changed the field. They showed through simulations that there are two fundamentally different ways gas falls into galaxies, and the boundary between them is determined by the mass of the galaxy's dark matter halo. Below a critical threshold of roughly 1 trillion solar masses, gas flowing along dark matter filaments can stream directly onto the galactic disk without ever being shock heated. It stays cold, around 10,000 Kelvin. It flows like a river along the filament, funneled by gravity, and crashes onto the disk, where it immediately begins forming stars. This is cold flow accretion. Above that critical mass, the infalling gas slams into the galaxy's existing hot halo and is shock heated to millions of degrees. It becomes too hot to collapse. Star formation throttles back. The galaxy begins to die. Deacle and colleagues expanded on this in the landmark 2009 paper in Nature. They showed that at high redshifts, when the universe was young, even massive galaxies were fed by cold streams. Typically 3 fairly narrow, fairly radial streams penetrated the hot halo, each delivering roughly 100 solar masses of fresh gas per year directly to the disk. These streams were not diffuse clouds drifting in from random directions. They were focused, channeled, delivered along the filaments of the cosmic web like water through pipes. The observational confirmation has been building steadily. In 2016, Christopher Martin's team used the Palomar Cosmic Web Imager to directly detect a rotating protodisk of pristine hydrogen at redshift 2.8, being actively fed by filamentary flows from the surrounding cosmic web. In 2023, Bjorn Emons and colleagues used ARMA, the Atacama Large Millimeter Array, to detect a stream of atomic carbon gas stretching 100 kiloparsecs, over 300,000 light-years, connected to radio galaxy 4C 41.17 at redshift 3.8. That stream contained enough fuel to sustain star formation for hundreds of millions of years. The cosmic web was caught in the act of feeding a galaxy. But feeding is only part of what the web does. It also tells galaxies which direction to spin. And that finding is one of the strangest results in modern astrophysics. The pattern was first seen in simulations by Codis, Pichon, and colleagues in 2012, and by Dubois and others in 2014, then confirmed observationally by Temple and Libeskind in 2013, and Welker and colleagues in 2020. It goes like this. Low-mass galaxies, the ones still growing, tend to spin with their rotation axis aligned parallel to the filament they sit on. They spin like wheels rolling along a track. But when a galaxy crosses a critical halo mass of roughly 5 trillion solar masses, something flips. The spin axis rotates 90 degrees. Massive galaxies spin perpendicular to their host filament. They spin like a top, balanced on the wire. This is called the spin transition, and it is explained by a theory called constrained tidal torque theory. When a galaxy is young and small, it acquires its angular momentum from the tidal field of the surrounding cosmic web. That tidal field is aligned with the filament, so the galaxy spins along it. But as the galaxy grows through mergers, and those mergers happen preferentially along the filament because that is where the neighboring galaxies are, the orbital angular momentum of the infalling objects converts into spin angular momentum perpendicular to the filament. The galaxy does not choose to flip. The web flips it. In December of 2025, this story took another turn. Lila Jung and colleagues discovered a structure that should not exist by any standard model of isolated galaxy formation. A razor-thin chain of 14 hydrogen-rich galaxies stretching 5.5 million light-years within a larger filament, all rotating coherently at roughly 110 kilometers per second, in sync with the filament itself. Not just aligned, synchronized. The filament was rotating, and the galaxies embedded in it were rotating with it, like beads on a spinning thread. This is one of the largest coherent rotating structures ever observed, and it was reported in tandem with earlier evidence from Wang and Libeskind in 2021 that cosmic filaments themselves may spin. Filaments, spinning, structures hundreds of millions of light years long, rotating as a unit. Think about what that means. The cosmic web is not just a static framework. It is dynamic. It feeds galaxies. It determines how they spin. It spins itself. And when a galaxy loses its connection to the web, the consequences are lethal. In 2019, Miguel Aragon Calvo, Mark Nairink, and Joseph Silk published a paper proposing what they called cosmic web detachment. The idea is elegant and grim. When the large-scale dynamics of the cosmic web cause shell crossing, the point where streams of matter from different directions intersect and disrupt a galaxy's primordial connection to its feeding filament, the supply of cold gas is severed. Star formation declines. The galaxy reddens, ages, and eventually becomes what astronomers call quenched. A red and dead elliptical, no longer forming new stars, slowly fading as its existing stars burn out. This is not a peripheral effect. Observations show that up to 45% of all galaxies fall into clusters via filaments, and many of them arrive already pre-processed, already stripped of gas, already quenched. The filaments did not just deliver them, the filaments shaped them during the journey. By the time a galaxy reaches a cluster, it has already been transformed by the web it traveled along. There is a common misconception, one that shows up in almost every popular science account of galaxy formation, that galaxies formed independently and then clustered together under mutual gravity. The truth is the opposite. The dark matter filaments formed first. Galaxies condensed along them afterward. The web is not a consequence of galaxy formation. It is the cause. Galaxies are not the main characters in this story. They are symptoms, products, side effects of a process that operates at scales hundreds of millions of light years across and is orchestrated by a substance we have never directly detected. And the Milky Way is not exempt. Your galaxy right now sits on a filament. A local sheet, a flattened structure of galaxies roughly 34 million light years across, is part of the larger Laniakea supercluster, which itself is a single gravitational basin in the cosmic web. High-velocity clouds of hydrogen are falling onto the Milky Way at about 0.2 solar masses per year. These clouds are fragments of cosmic web gas condensing out of the warm, hot intergalactic medium that permeates the filaments. The Milky Way needs roughly 1 solar mass of new gas per year to sustain its current rate of star formation. The high-velocity clouds provide only a fraction of that. The rest is likely coming from the gradual cooling of the galaxy's hot corona, which is itself replenished by the web. Without the filament, the Milky Way starves, star formation slows, new planets stop forming. Over billions of years, the galaxy dims. The cosmic web is not something you can observe from a comfortable distance. It is the thing keeping you alive. Now consider what all of this means in the context of the missing baryon problem, because this was until very recently one of the most embarrassing open questions in Cosmology. The Big Bang produced a specific amount of ordinary matter, baryons, protons and neutrons. We know exactly how much, because the cosmic microwave background, the afterglow of the Big Bang, measured to extraordinary precision by the Planck satellite, tells us. Roughly 5% of the total mass energy of the universe is ordinary matter. The rest is dark matter and dark energy. But when astronomers added up all the ordinary matter they could find, all the stars in all the galaxies, all the gas in galaxy clusters, all the interstellar and circumgalactic medium, the total came to only about half of what should exist. Roughly 40 to 50% of all ordinary matter in the universe was simply missing. Not dark matter, normal matter, protons and neutrons that the Big Bang produced but that nobody could find. The prime suspect was always the warm-hot intergalactic medium, the WIM. Theoretical models predicted that vast quantities of ordinary gas, heated to temperatures between 100,000 and 10 million Kelvin, should be spread through the filaments of the cosmic web, too hot to show up in ultraviolet surveys, too cool and too diffuse to register in X-ray telescopes, just sitting there in the spaces between galaxies, invisible by every conventional method. The breakthrough came in 2017, when two independent teams detected this gas using the same technique, the thermal Sunyaev-Zeldovich effect. When photons from the cosmic microwave background pass through hot gas, the electrons in that gas boost the photon's energy by a tiny but measurable amount. Hideki Tanimura at the University of British Columbia stacked Planck satellite data between 262,864 pairs of luminous red galaxies. Independently, Anna de Graaf at the University of Edinburgh stacked data between over 1 million galaxy pairs. Both teams found the signal. De Graaf's detection reached 5.1 sigma significance. The gas was there. It was exactly where the model said it would be, threaded through the filaments at a temperature of roughly 2.7 million Kelvin. But the definitive proof came from an entirely different direction: fast radio bursts. These are millisecond duration blasts of radio waves from cosmological distances, most likely produced by magnetars. When a fast radio burst travels through ionized gas, different frequencies of the radio wave travel at slightly different speeds, creating a measurable delay called dispersion. The more ionized gas the burst passes through, the greater the dispersion. In 2020, Jean-Pierre Macquart and colleagues used the ASCAP radio telescope in Australia to measure the dispersion of just 6 localized fast radio bursts, and showed that it correlated with redshift exactly as predicted if the full baryon budget exists as diffuse ionized intergalactic gas, the Macquart relation. Macquart himself declared they had used fast radio bursts to weigh all the matter in the universe and found the half that was missing. Macquart died in 2020, just months after the paper was published. He was 49. By 2025, the picture was essentially complete. Liam Connor and Vikram Ravi extended the analysis to 60 localized fast radio bursts and showed conclusively that approximately 76% of all baryonic matter in the universe resides in the intergalactic medium, the gas-permeating cosmic web filaments. In June of 2025, Konstantinos Mikas and colleagues achieved the first clean X-ray spectroscopic detection of pure WIM emission from a single filament in the Shapley supercluster, a structure 23 million light-years long with gas at roughly 10 million degrees. The missing baryons were never missing. They were hiding in the filaments, in the cosmic web, in the very structure that we can photograph but whose dominant component we cannot identify. So let me draw the picture for you as it stands right now, because the next part of this requires you to hold the whole thing in your mind at once. The universe has a structure. It is a web of filaments and nodes and voids, stretching across the entire observable universe. The filaments contain half the mass of the cosmos. They feed galaxies with rivers of cold gas. They determine how galaxies spin. They control when galaxies die. They hold the ordinary matter that was missing for decades. They are dynamic, evolving, possibly rotating at scales of hundreds of millions of light years. 85% of the mass in these filaments is a substance we have never detected. Despite 92 years of trying, every major detection experiment has returned null results. The most sensitive instrument ever built, running for over a year in a mine a mile underground, found 0 particles of it. And the pattern this substance has built across the observable universe is quantitatively identical by peer-reviewed spectral analysis to the pattern of neurons inside a human brain. That is not a metaphor. That is not a visualization choice. That is not a poetic observation made by a science communicator trying to make the cosmic web sound interesting. That is a published, quantitative result. And what it implies about the nature of reality is something that should have made headlines in every country on Earth. It did not. It was published, peer-reviewed, and quietly filed away. Here is what Franco Vazza and Alberto Fleti actually found. Vazza is an astrophysicist at the University of Bologna. He studies the cosmic web. Specifically, he studies its complexity, the information content of large-scale structure, and the thermodynamic processes that shape filaments and cluster outskirts. Fleti is a neurosurgeon at the University of Verona. He operates on human brains. He maps the structural organization of neural tissue, the way neurons cluster, branch, and connect in patterns that give rise to consciousness, memory, and thought. These two men had never collaborated before. They had no particular reason to. Their fields are separated by the entire span of science, from the largest scales to the smallest, from structures that take billions of years to form, to signals that fire in milliseconds. But Vazza had noticed something in his simulations that he could not stop thinking about. When you zoom out on a cosmological simulation far enough that individual galaxies become points, and the dark matter filaments connecting them become visible threads, and the voids between them become dark bubbles, the image you get looks like something. Not abstractly, not if you squint. It looks, with uncomfortable specificity, like a microscope image of neural tissue, the branching patterns, the density of connections at the nodes, the ratio of clustered matter to empty space, the threads and the junctions and the gaps between them. Vazza had seen this visual resemblance and done what a careful scientist does when a visual resemblance bothers them. He quantified it. He contacted Fleti. They obtained high-resolution images of the human cerebellum and cerebral cortex, sliced at 4 and 40 micrometer thicknesses, stained to reveal the neuronal network in detail. They obtained matched slices from cosmological simulations, specifically the output of magneto-hydrodynamical models of the cosmic web, at scales from 5 megaparsecs to 500 megaparsecs. And then they applied the same mathematical tool to both, power spectrum analysis. This is a standard technique in cosmology, used for decades to characterize the distribution of matter in the universe. You decompose a density field into its component spatial frequencies, like breaking a piece of music into its individual notes. And you measure how much structure exists at each scale. The result is a curve. The shape of that curve tells you everything about how matter is organized in the system you are studying. If two systems have the same power spectrum, they have the same organizational architecture. They are built the same way. When Vaza and Fleti computed the power spectrum of the cerebellum on scales from 1 micrometer to 0.1 millimeters and compared it to the power spectrum of the cosmic web on scales from 5 million to 500 million light years, the two curves fell on top of each other, not approximately, not with generous error bars and a sympathetic reading. The spectral density distributions overlapped within the measurement uncertainty. The cerebellum matched the cosmic web more closely than the cerebral cortex did, which is itself a telling detail, because the cerebellum has a more regular, parallel, filamentary microstructure, more closely resembling the thread-like organization of cosmic filaments than the folded sheet-like architecture of the cortex. The cortex showed a similar but slightly different spectrum. Both were closer to the cosmic web than to any other comparison system the authors tested. Let that sit for a moment. These are two systems separated by 27 orders of magnitude, 27 powers of 10. If you wrote out the ratio of their sizes as a number, it would have 27 zeros after the one. One system is measured in millionths of a meter. The other is measured in billions of light years. One runs on electrochemistry and takes milliseconds to fire a signal. The other runs on gravity and takes billions of years to evolve a single filament. One weighs about 1.4 kilograms and fits inside a human skull. The other contains roughly 10 to the 53rd kilograms of mass and spans 93 billion light years. They have no known physical connection, no shared mechanism, no causal link, and their density fluctuation spectra, the mathematical fingerprint of how matter is distributed at different scales within each system, are indistinguishable. The authors were careful in their paper, published in Frontiers in Physics in November of 2020. They did not claim that the universe is a brain. They did not claim that the cosmic web thinks or feels or is aware. What they said, precisely, is that the two systems appeared to share common organizational principles. Both are self-organizing networks. Both produce filamentary structures connected at dense nodes. Both dedicate approximately the same fraction of their total mass to the active structural component, roughly 30%, with the rest playing a supporting or passive role. In the brain, neurons make up about 30% of the total cell count and mass, with the remainder being glial cells, water, and support structures. In the universe, galaxies and the dark matter filaments connecting them make up roughly 30% of the total mass energy budget, with the remaining 70% being dark energy, a component that does not participate in structure formation. But it was the power spectrum match that was genuinely difficult to explain away, because the comparison was not just between the cosmic web and the brain. Vaza and Fleti also compared both systems to other complex structures: clouds, tree branches, turbulent plasma, river networks, crystal lattices, water ice. In every case, the other systems produced different spectra, most of them steeper, consistent, with fractal or quasi-fractal organization. The brain and the cosmic web did not follow that pattern. They were both non-fractal. Both showed a specific pattern of scale-dependent organization, with characteristic clustering at particular size ratios that none of the other complex systems shared. The cosmic web and the brain occupied their own region of parameter space, separate from everything else the authors tested. This matters because fractals are common. Nature produces them constantly and effortlessly. Coastlines, lightning bolts, blood vessels, mountain ridges, river deltas, tree canopies, all fractal. A fractal system looks roughly the same at every scale. Zoom in and you see the same pattern repeating endlessly, a property mathematicians call self-similarity. The brain and the cosmic web do not do this. They are structured differently at different scales, in specific ways, and those specific ways match each other while diverging from every other comparison system Vaza and Fleti tested. Clouds showed steeper spectra. River networks showed steeper spectra. Crystal lattices, turbulent plasma, water ice, all steeper, all fractal or quasi-fractal. Only the brain and the cosmic web sat together in that particular region of the parameter space, with that particular spectral slope, sharing that particular pattern of scale-dependent clustering. That is not what you would expect from two unrelated systems that just happen to be complex. That is what you would expect from two systems governed by the same underlying organizational dynamics. And so far, nobody has identified what those dynamics are. Vazza went further. He estimated the information content of both systems. By information, he means something precise. Claude Shannon's mathematical definition from 1948, the minimum amount of data required to describe the state of the system at the scale where its self-organized structure emerges. For the observable universe, Vazza estimated that between 1 and 10 petabytes of information encode the cosmic web's filamentary architecture, its full network topology of nodes and connections, and voids. Independent estimates of the human brain's memory capacity based on the number of synapses, approximately 100 trillion. And the information stored at each one converge on roughly 2.5 petabytes. 1 to 10 petabytes for the cosmic web, 2.5 petabytes for the brain. The same order of magnitude for two systems that share no physics, no chemistry, no biology, and no history. Only the shape of their networks and the mathematics that describe them. I need to be precise here about what this does and does not mean, because precision is the difference between unsettling science and irresponsible speculation. Vaza and Fleti are not claiming the universe processes information the way a brain does. They are not claiming the cosmic web is conscious. They are not claiming that dark matter filaments carry signals the way axons carry nerve impulses. The cosmic web does not fire. It does not think. It does not experience anything, as far as anyone can determine. What they are claiming, and what the data supports, is that there appears to be a universal principle governing how self-organizing networks structure themselves, a principle that operates independently of scale, material, and mechanism. The brain arrives at its architecture through electrochemistry and natural selection over hundreds of millions of years. The cosmic web arrives at its architecture through gravity and cosmic expansion over billions of years. Both end up in the same place. Both produce the same mathematical signature. The question nobody has answered is why. And this is where the story connects to a thread in theoretical physics that most popular science accounts avoid entirely, because it sounds too much like philosophy. It is not philosophy. It is published physics. And it starts with a man named John Archibald Wheeler. Wheeler was one of the most important physicists of the 20th century. He worked with Niels Bohr on the liquid drop model of nuclear fission in 1939. He supervised Richard Feynman's PhD thesis at Princeton. He coined the terms black hole and wormhole. He collaborated with Albert Einstein on unified field theory. He was, by any measure, an establishment figure, a man whose work had shaped the field for 50 years, and he spent the last decades of his career consumed by a single question that most of his younger colleagues considered unanswerable and possibly unscientific. What is the relationship between information and physical reality? In 1989, Wheeler delivered a lecture at the Santa Fe Institute in which he proposed what he called it from bit. His claim was that every physical quantity, every particle, every field, every space-time interval derives its existence from the answers to yes or no questions. Binary choices. Bits. The universe, Wheeler argued, is not a machine made of matter that happens to contain information as a byproduct. It is information. Information is what gives rise to what we experience as matter, energy, and space. The bit is more fundamental than the atom. Physics is not about stuff. Physics is about the answers to questions posed by the act of measurement. Wheeler drew a diagram he called the participatory universe, a U-shaped symbol with an eye at one end, observing the other, illustrating his conviction that the universe and the observer create each other through the exchange of information. His colleagues were polite about it. Many of them thought he had gone soft in his old age. Wheeler died in 2008 at 96. Within a decade, the informational view of physics he championed had moved from the fringe to the center of theoretical research. In 2002, Seth Lloyd at MIT published a paper in Physical Review Letters titled Computational Capacity of the Universe. Using the Bekenstein bound, the theoretical maximum amount of information that can be contained in a given region of space, and the Margulis-Levitin theorem, which sets the maximum speed at which information can be processed, given a finite amount of energy. Lloyd calculated that the observable universe has performed no more than 10 to the 120th operations on approximately 10 to the 90th bits since the Big Bang. Those numbers are large, but they are finite. The universe has a computational budget. It has done a specific amount of processing and no more. Every interaction between every particle since the beginning of time is a computation. Every gravitational collapse, every nuclear reaction, every photon absorbed and re-emitted, all of it is information being processed. And the total, across all of space and all of time, is a number you can write down. The universe, in a precise and defensible mathematical sense, is a quantum computer. It is not like a computer. It is one. It is a physical system that processes information according to the laws of quantum mechanics, and the output of that processing is the entire physical world. Every particle, every field, every structure, every galaxy on every filament of the cosmic web, every neuron in every brain that has ever existed. The computation and the reality are not separate things. They are the same thing described in two different languages. The holographic principle, proposed by Gerard 't Hooft in 1993 and formalized by Leonard Susskind in 1995, pushes this even further. It states that the total information content of any region of three-dimensional space can be fully encoded on the two-dimensional boundary surface of that region at a maximum density of approximately 1 bit per Planck area, which is roughly 10 to the minus 66 square centimeters. A single Planck area is so small that a proton contains roughly 10 to the 40th of them. The three-dimensional interior, everything you experience as volume and depth and spatial extension, is, in some precise sense, that physicists are still working to fully articulate, a projection of the information living on the boundary. The universe may be a hologram, not in the science fiction sense of a flickering image projected from a hidden device, in the mathematical sense that the information required to describe a three-dimensional volume is equivalent to the information that can be stored on its two-dimensional surface. Juan Maldacena's 1997 conjecture, the ADS/CFT correspondence, provided the first concrete proof of concept. He showed that a universe with gravity in 5 dimensions is exactly equivalent, not approximately, exactly, to a quantum field theory without gravity living on its 4-dimensional boundary. That paper has been cited over 23,000 times. It is the most cited paper in the history of high-energy physics, and its deepest implication is that the three-dimensional world you navigate every day may be encoded on a distant surface you can never reach or observe directly. Vazza himself has been pushing on the information angle. In a 2017 paper in the monthly notices of the Royal Astronomical Society, he applied Shannon information measures to cosmological simulations and showed that the most informationally complex environments in the universe, the regions with the highest information content per unit volume, are the peripheries of galaxy clusters and the surfaces of filaments, the places where multiple physical processes collide, where cold gas meets hot gas, where gravitational infall meets thermal pressure, where merging structures create shocks and turbulence that generate entropy at extraordinary rates. These are the edges, the boundaries, the skins of the cosmic web's filaments and nodes. And if the holographic principle is correct, boundaries are precisely where information lives. The cosmic web's information peaks at its surfaces. The holographic principle says all information lives on surfaces. The brain's information processing concentrates at the surfaces of neurons, at the synaptic junctions where signals pass from one cell to another. The same architectural principle, the same geometry, at scales separated by 27 orders of magnitude. In 2012, before the Vazza-Fleti comparison was even conceived, Dmitry Kryukov and colleagues at the University of California, San Diego, published a paper in Scientific Reports titled Network Cosmology. They demonstrated mathematically that the causal structure, space-time, the set of all points in the universe's history that can influence each other given the finite speed of light and the finite age of the cosmos, forms a power law graph with strong clustering. This is a specific mathematical object. It has measurable properties: degree distribution, clustering coefficient, average path length, community structure. And when Kryukov's group measured these properties for the causal network of space-time and compared them to the measured properties of neural networks in biological brains, the Internet's router-level topology, and large-scale social networks, They found the same values, the same degree distributions, the same clustering coefficients, the same community structure, not approximately, within measurement uncertainty. The reason, Kryukov argued, is geometric, a network that grows by adding nodes in an expanding hyperbolic space, where new nodes preferentially connect to nearby existing nodes, will naturally produce this specific topology regardless of what the nodes physically are. Neurons in a developing brain are added over time in a space that is effectively hyperbolic from the network's perspective. Galaxies in an expanding universe are added over time in a space that is literally hyperbolic, because the de Sitter space-time that describes our accelerating cosmos has hyperbolic spatial geometry. The dynamics are the same. The math does not care whether the nodes are cells or galaxies. It only cares about the geometry of the space they grow in and the rules by which they connect. The laws that govern how neurons wire together in a developing brain may be the same laws expressed at a different scale and in a different medium that govern how dark matter filaments wire together in an expanding universe. Nobody has proved this. Nobody has disproved it. The data sits in a collection of peer-reviewed journals across 4 different fields of science, and the number of researchers actively working on the connection between cosmic structure and neural architecture could fit in a small seminar room. The finding that should have catalyzed an entirely new field of research instead became a curiosity, a fun fact for science communicators, a comparison image that gets shared on social media every few months with a caption about the universe looking like a brain, and then is forgotten by the next news cycle. Think about what we are actually saying here. We have a published, peer-reviewed, quantitative demonstration that the largest structure in the observable universe and the most complex biological structure ever examined produce the same mathematical signature. We have a separate, independently derived demonstration that network growth in expanding spaces produces the same topology regardless of whether the network is made of neurons, websites, or space-time events. We have a calculation showing that the information content of the cosmic web and the information capacity of the human brain are within the same order of magnitude. We have a theoretical framework, the holographic principle, supported by the most cited paper in the history of string theory, that says information is more fundamental than matter and lives on boundaries. And we have the discoverer of the cosmic web's information structure, Vazza himself, showing that the boundaries and surfaces of filaments are where the universe's information complexity peaks. Each of these findings, taken alone, could be dismissed as coincidence or as an artifact of how networks self-organize in general. Taken together, they form something that is considerably harder to wave away. They form a pattern, and the scientific establishment's response to that pattern has been overwhelmingly to not respond at all. There is a word for this in the sociology of science. It is called the Planck principle, after Max Planck's observation that science advances one funeral at a time. New ideas do not win by convincing their opponents. They win because their opponents eventually die, and the new generation grows up that finds the ideas familiar. The cosmic web-brain connection is not even at the stage where it faces active opposition. It is at a stage before that, a stage where the finding is simply not engaged with, not because anyone has shown it to be wrong, but because it does not fit into any existing research program, any existing funding structure, any existing career path. There is no department of cosmic neurology. There is no grant program for studying why the universe's filament network matches the brain's neural network. There is no tenure-track position for the question that sits at the intersection of cosmology, neuroscience, information theory, and network science. The question falls between disciplines the way light falls into a gap between floorboards, and so it goes unasked, not suppressed, neglected, which in practice produces exactly the same outcome. This is not the first time this has happened in this story. Zwicky's dark matter was not suppressed, it was neglected. For 40 years, Rubin's rotation curves were not suppressed. They were received by a community that did not want to reckon with what they implied, and so chose, collectively, to look elsewhere. Geller and Huchter's bubble structure was not suppressed. It was greeted with shock and then inadequately credited. The pattern of neglect runs through the entire history of the cosmic web like a thread of its own, an invisible filament connecting every major discovery to the same institutional response. We see it, we confirm it, and then we find reasons not to think about what it means. And the quiet burial of the Vaza-Fleti result is arguably the most consequential instance yet, because this is not about one anomalous observation that might have a mundane explanation. This is about the convergence of 4 independent lines of evidence from 4 different subfields, all pointing toward the same conclusion: the power spectrum match, the non-fractal exclusivity, the information capacity convergence, the network topology equivalence. Each alone could be dismissed as coincidence. Together, they form something that no working scientist has been able to explain away, and no working scientist has been willing to build a career around investigating. The mathematical architecture of the cosmic web and the mathematical architecture of the human brain are the same. That finding sits in the journals like an unexploded bomb that everyone has agreed to walk around, because underneath all of it, underneath the filaments and the nodes and the voids, underneath the galaxies that formed along dark matter scaffolding laid down in the first fraction of a second after the Big Bang, underneath the gas that flows through the web like blood through capillaries, underneath the missing baryons that hid in the warm-hot intergalactic medium for decades before anyone found them, there is the substance itself, the dark matter, the thing that accounts for 85% of the web's mass, that shaped every structure larger than a galaxy, that determined the architecture of the cosmic network, and that has never been identified by any experiment in 92 years of searching. We can photograph what it built. We can simulate its effects to extraordinary precision. We can measure its gravitational fingerprint in the warped light of distant galaxies. We can watch it feed, spin, and kill the galaxies that formed along its threads. We can run the same mathematical analysis on its network and on the neurons in a human brain and get the same curve. We can calculate the information content of both systems and find the same number, and we do not know what it is. We do not know if it is a particle, a field, or something that does not fit into any category physics currently recognizes. After 92 years, the question Fritz Zwicky asked in his basement office at Caltech has still not been answered. That is where things stand as of right now. And what has happened in the past 3 years has not resolved this tension. It has made it considerably worse. In June of 2023, the James Webb Space Telescope discovered one of the earliest cosmic web filaments ever observed, a thread of 10 galaxies stretching 3 million light-years. existing just 830 million years after the Big Bang. This was part of the ASPIRE survey, led by Feige Wang, which used JWST's near-infrared spectrograph to peer into the epoch of reionization, the period when the first stars and galaxies switched on and began ionizing the neutral hydrogen that had filled the universe since the cosmic dark ages. The filament was anchored by a luminous quasar at redshift 6.6, and its existence at such an early epoch confirmed what simulations had been predicting for decades, but no telescope had been able to verify. The cosmic web was already forming when the universe was barely 6% of its current age. The dark matter scaffolding was going up before most of the galaxies that would eventually live on it had begun to coalesce. The architecture came first. The inhabitants came after. That alone would have been enough to reshape the timeline of structure formation. But JWST found something else, something that may turn out to be far more consequential to the question of what dark matter actually is. Many of the young galaxies JWST observed at redshifts between 3 and 8, galaxies existing when the universe was between roughly 700 million and 2 billion years old, were prolate, elongated, shaped like cigars or rugby balls rather than the disks and spheres that dominate the local universe. This was not expected. In the standard cold dark matter model, galaxies at those epochs should be building themselves through chaotic mergers, collisions from random directions that average out asymmetries and produce relatively round shapes. Prolate morphology suggests something different. It suggests galaxies being stretched along filaments during formation, their shapes determined not by random collisions, but by the anisotropic tidal field of the cosmic web itself. The web was not just hosting these galaxies, it was sculpting them, pulling them into alignment with its own geometry, like clay drawn along a wire. In 2025, Anastasia Pozzo and colleagues published an analysis in Nature Astronomy that made this observation considerably more pointed. They showed that the observed distribution of prolate galaxy shapes at high redshift is not reproduced by standard cold, dark matter simulations. The models that best match what JWST actually sees use warm dark matter or wave dark matter, also called fuzzy dark matter. These are alternative forms of dark matter in which the particle has a very small mass on the order of 10 to the minus 22 electron volts and correspondingly large quantum wavelength. At these masses, quantum effects operate on astrophysical scales. The dark matter behaves less like a collection of individual particles and more like a wave, with interference patterns that suppress small-scale structure and change how filaments and young galaxies interact. If this result holds up, as JWST accumulates more data over the coming years, it would be the first observational constraint on the particle nature of dark matter derived not from a detector buried underground, not from a particle collider smashing protons together at the speed of light, but from the shapes of galaxies 11 billion light-years away, the shapes that the cosmic web impressed upon them during their formation. The cosmic web, the thing dark matter built, would be telling us what dark matter is. The architecture would be revealing the nature of the architect, and the answer would not be a wimp. It would be something stranger, something quantum mechanical at astrophysical scales, something that blurs the line between particle and wave across millions of light years. And that is not the only direction from which the standard model is taking fire. In March of 2025, the DESI collaboration released its Data Release 1, the largest three-dimensional map of the universe ever produced. 18.7 million spectroscopic objects, nearly 15 million galaxies and quasars with precisely measured redshifts, mapping the expansion history of the universe back 11 billion years. DESI tracks the baryon acoustic oscillation signal, a relic of sound waves that propagated through the hot plasma of the early universe and left a characteristic imprint on the distribution of galaxies. By measuring how the size of that imprint changes with distance and cosmic time, DESI can reconstruct the expansion rate of the universe at different epochs with extraordinary precision. Its Year 1 results, published in April of 2024, had hinted at something unexpected. Its Year 3 results, with nearly 3 times the data, strengthened those hints to the point where they can no longer be comfortably ignored. Dark energy appears to be evolving. The standard cosmological model treats dark energy as a cosmological constant, Einstein's lambda, a fixed energy density woven into the fabric of space-time that does not change, does not dilute, does not vary with time or location. This is the simplest possible explanation for the observed acceleration of the universe's expansion, and for 25 years it has been the default assumption of nearly every cosmological model and simulation. DESI's data suggests it may be wrong. The equation of state parameter W, which equals -1 for a true cosmological constant, appears to be changing over cosmic time. It was less negative in the distant past, closer to 0, and has become more negative in the recent universe. The trend is consistent across multiple independent tracer populations in the DESI data. It is consistent with hints from the Planck satellite and from Type Ia supernova surveys. It is not yet at 5 sigma, but it has strengthened with every new data release, and the trajectory is pointing toward a conclusion that would shatter the foundation the standard model is built on. If dark energy is evolving, the implications do not stay contained within cosmology. They cascade through everything. The expansion rate of the universe changes at different epochs, which means the rate at which dark matter filaments grow and merge changes. The timing of structure formation shifts. The environments in which galaxies form, evolve, and die are altered in ways that propagate through every prediction the standard model has ever made. The ultimate fate of the universe, whether it expands forever and cools to absolute zero, whether it reverses into a collapse, whether it accelerates until every bound structure is torn apart in a big rip, depends entirely on what dark energy does in the future. And if dark energy is not constant, we cannot predict that future. The forecast is gone. We have built every simulation of the cosmic web, every model of structure formation, every prediction about the lifespan and death of galaxies on the assumption that dark energy is a fixed number. If DESI is right, then the scaffolding of reality is not just built from an unknown substance. It is being reshaped by an unknown force whose behavior changes over time in a direction we cannot forecast with current physics. 95% of the universe is dark matter and dark energy, one substance we cannot identify, one force we may not even be able to describe with a constant. Together, they account for nearly everything that exists. And as of 2025, we understand neither of them. Meanwhile, ESA's Euclid Space Telescope is quietly assembling the dataset that will test all of this. Launched in July of 2023 to the L2 Lagrange point, Euclid carries a visible light camera and a near-infrared spectrometer designed to measure the shapes and redshifts of over 1 billion galaxies across 14,000 square degrees, roughly a third of the entire sky. Its first quick data release in March of 2025 covered 63 square degrees and contained 26 million galaxies, observed out to 10.5 billion light-years, along with 500 gravitational lens candidates. Early analysis papers confirmed that more massive galaxy clusters connect to more cosmic web filaments, a basic prediction of structure formation theory that had never been tested at this precision. They also showed that elliptical galaxies preferentially align their long axes with the filaments they inhabit, adding another data point to the growing evidence that the web physically shapes the galaxies that live on it. But Euclid's real contribution is still ahead. Its full survey will produce the first comprehensive three-dimensional dark matter map of the observable cosmos, using weak gravitational lensing measurements of over 1 billion background galaxies to trace the invisible scaffolding directly. It will measure how the cosmic web has evolved over the past 10 billion years. It will test whether the dark matter distribution matches the predictions of cold dark matter, or whether, like JWST's prolate galaxies and DESI's evolving dark energy, it points towards something the current model cannot accommodate. And then there is the Vera Rubin Observatory, perched on Cerro Pachon in the Chilean Andes, carrying an 8.4-meter primary mirror and the largest digital camera ever constructed, 3.2 billion pixels. It began its commissioning phase in 2024. Its 10-year legacy survey of space and time will observe approximately 20 billion galaxies, producing the deepest, widest imaging survey ever conducted. Its core science goals are to map dark matter and dark energy with enough precision to determine whether the cosmological model holds or breaks. The telescope is named after the woman who confirmed dark matter with 21 galaxy rotation curves and was denied the Nobel Prize. The observatory that carries her name will be the instrument that tests whether the model her work helped build is correct. If the model breaks, it will break under her name. There is a justice in that, a delayed, inadequate, deeply human justice, because the history of the cosmic web is, in the end, a history of seeing what was always there and being told it did not matter. Zwicky saw the invisible mass in 1933 and was exiled to a basement office while his colleagues wrote rules specifically to keep him away from the best telescope. He died in 1974 without seeing his discovery confirmed. In 2024, 91 years after his original measurement, a team directly imaged dark matter filaments in the same coma cluster he had studied. Same cluster, same invisible mass, same unanswered question. Rubin measured flat rotation curves in galaxy after galaxy, provided some of the most important observational evidence in modern cosmology, and was denied the highest honor in science because of her gender. She died on Christmas Day in 2016. The observatory named after her will soon test whether the model she helped build survives the decade. Keller mapped the large-scale structure of the universe, received a MacArthur Fellowship for her work, and was never given tenure by the institution where she made the discovery. Hutra observed 130 nights in a single year, kept his Teamsters dues current in case astrophysics failed, cooked Thanksgiving dinners for students who had nowhere else to go, and died at 60, one of a heart attack. Makar weighed all the ordinary matter in the universe using fast radio bursts and died at 49 months after publishing the result. Kaufman coined the term cosmic web in a Nature paper and died at 52 before the term became standard in textbooks. And Vaza and Fleti published a paper demonstrating that the mathematical architecture of the cosmic web is identical to the mathematical architecture of the human brain. And the scientific establishment responded with what can only be described as a collective shrug. The pattern is there. The data is there. The convergence of independent findings from cosmology, neuroscience, information theory, and network science is there. The largest structure in the observable universe produces the same power spectrum as the most complex biological structure ever examined. It is built from a substance that has evaded every detector in 92 years. Its information content matches the information capacity of a human brain to within an order of magnitude. Its network topology is mathematically equivalent to neural networks in a result derived independently by a completely different research group using completely different methods. And the theoretical framework connecting information to physical reality, Wheeler's it from bit, Lloyd's computational universe, Maldasena's holographic principle, is not speculative philosophy. It is published, peer-reviewed, heavily cited physics. None of this proves that the universe is a brain. The cosmic web does not think. It does not feel. It does not experience. That claim is not supported by the data, and I am not making it. What the data does support, and what nobody has been able to refute, is that there exists an organizational principle operating across at least 27 orders of magnitude in scale that produces the same non-fractal, filamentary, node-connected architecture in both the largest and most complex structures known to exist. That principle has not been identified. It has not been named. It has not been explained. It has barely been investigated. The comfortable response is to call it coincidence. Self-organizing networks converge on similar structures regardless of scale. And the brain and the cosmic web are just two examples. That response is not wrong. It may even be correct, but it explains nothing. Saying that two systems share organizational principles is a description dressed as an explanation. It does not tell you why those particular principles produce that particular structure at those particular scales and no others. It does not tell you why the match is non-fractal when most complex systems are fractal. It does not tell you why the information content lands in the same range. It does not tell you anything you did not already know from looking at the data. It just gives you permission to stop thinking about it. The uncomfortable response is that the resemblance is a clue. That information, in Wheeler's sense, is more fundamental than the matter it organizes. That the reason the cosmic web looks like a brain is not because networks are generic and nature is repetitive, but because the universe structures information in a specific way. And both the cosmic web and the neural network are expressions of that deeper principle. That the pattern of the cosmic web was encoded in quantum fluctuations during the first fraction of a second of existence. That the pattern of the brain was encoded in DNA shaped by 4 billion years of evolution on a planet sitting on a filament of that same web, and that the mathematical identity between the two patterns is not an accident to be dismissed, but a signal to be followed. nobody is following it. The question sits in the journals, unanswered and largely unasked, while the telescopes continue to collect data that makes the web bigger, the dark matter more mysterious, and the resemblance harder to ignore. Within this decade, Euclid will map the dark matter distribution across a third of the sky. The Rubin Observatory will image 20 billion galaxies. DESI will complete its 5-year survey and deliver a verdict on whether dark energy is constant or evolving. LZ's successor experiments will push into the neutrino fog and either find the dark matter particle or close the door on the WIMP hypothesis for good. JWST will continue peering into the earliest epochs of cosmic web formation, watching the scaffolding assemble itself in real time 11 billion years after the fact. Every one of those results will sharpen the picture, and every one will make the unanswered question more urgent, because the more precisely we map the web, the more clearly the pattern emerges, and the more clearly the pattern emerges, the harder it becomes to look at it and not see what Vaza and Fleti saw: a network, nodes and threads, the architecture of a mind written across the sky in a substance we cannot name. The pattern of the cosmic web was set in the first trillionth of a second after the Big Bang. Quantum fluctuations in the inflaton field stretched across the entire sky by inflation, imprinted on matter, amplified by gravity over 13.8 billion years. Every filament, every void, every node exists where it does because of a quantum event that occurred when the observable universe was smaller than a proton. The web remembers. It carries the imprint of the beginning in every thread, at every junction, across every billion light years of its structure. The initial conditions of the universe are still visible, frozen into the positions of galaxies and the shapes of voids, a memory written in dark matter that has persisted for almost 14 billion years. And that structure is you. You are a pattern of electrical signals in a network of 86 billion neurons inside a skull on a planet orbiting a yellow dwarf star, in a spiral galaxy sitting on the local sheet, on a filament of dark matter feeding into the Laniakea supercluster, inside a web that stretches across 93 billion light-years and connects every galaxy that has ever existed or ever will. The pattern your neurons form and the pattern your galaxy sits on produce the same curve when you subject them to the same mathematical analysis. 85% of the mass composing the larger pattern has never been detected by any instrument in human history. The mathematical identity between the two patterns has never been explained by any theory ever proposed. The universe is not empty. It was never empty. It is wired. Every galaxy tethered to every other galaxy by threads of something we cannot name, arranged in a pattern we cannot explain, identical to the one structure in nature that is capable of producing awareness, memory, and thought. And you are inside it.